Hi, welcome to the last talk of the platform track of Qt World Summit 2021. We're going to discuss data encryption in Qt applications, why it matters, and what it takes to protect data end-to-end. I'm Alexey Rusakov, a member of the technical governance team of Matrix.org and the lead developer of the Quotient project that enables application development for Matrix using Qt. My co-speaker today is Tobias Fella, a developer of NeoChat, the official Matrix client application for KDE. I will start with the brief preface bringing up the case for data encryption. Then I will talk about the kinds of data encryption that have to be considered and the situations where data encryption can be avoided altogether. And then I will hand over to Tobias to share a bit of implementation experience when adding end-to-end encryption to NeoChat. While we are talking, feel free to write down the questions in the chat and we will do our best to respond to those questions in real time. Or come to the speaker's lunch after the session. We will have 30 more minutes to discuss your questions in more detail. Before I get to the subject, let me give a few disclaimers so that you don't waste your time if that doesn't fly your spaceship. First of all, we are no security experts. We are encryption users in a way. We're common developers like most of you, and we're sharing our experience here. But if you have profound security background, then probably this session is not for you. You won't bring out anything new from it. There are no ready-made recipes here. We are sharing rather tips and tricks and general approaches, and it's up to you to apply those approaches in your specific setting. And we are not responsible if you do it wrong. Privacy is a separate story. Encryption does help privacy a lot, but privacy is a comprehensive topic that goes beyond just technical matters, and it can easily consume another 30 minutes of the discussion. Now let me give a few ground points of sorts. First of all, regardless of what I said or will say, but I will say pretty much the same along the way, never try to make your own crypto algorithms. That's a bad idea. There is an active, ongoing scientific research in the area, and no matter what you are trying to devise or even implement, will likely be inferior to what has already been done by people much more proficient than you. If you feel more proficient than that, then again, probably you are on the wrong track as of right now. Still, even if you're just an encryption user, mind what crypto you're using. There are broken and weak algorithms. There are algorithms that have to be applied in certain situations, and some algorithms should not be applied in those. Be mindful what is happening. And finally, when dealing with multiple layers, do not expect that you can protect on a single layer. Practice security in depth. I won't repeat that further in the talk. It's not exactly about this subject, but treat every layer as other layers are broken. That's a very useful practice to ensure that your security is really robust. Now, why would an ordinary developer have to encrypt data? There might be formal reasons, like legislation, GDPR in Europe, which basically implies that you encrypt all kinds of personally identifiable data at the very least. And then there are internal regulations that go from your own company, for example, that defines what kinds of data should be protected, should be encrypted, and probably even in which way. Check your documents. Aside from that, there are also just purely practical reasons. One of them is privacy. No matter if you consider yourself to be liable under GDPR conditions, consider yourself being liable if you're a developer, you have to simply consider what is happening with the data that you are storing and what might go wrong with the data that you are storing and what people, the data on whom you are storing, might end up in if the data gets leaked. Then there is intellectual property and sensitive data protection, where you naturally want to keep certain things to yourself and not disclose them to anyone, competitors or anyone else. And then there is pure data security. You just want to manage what kind of information is accessed by whom, for maybe which purpose, with what mandate, and so on and so forth. Now, regarding the kinds of data protection, let me start with the simplest thing with the simplest way to protect the raw data. It is really to not pass or store them at all. Before thinking of any kind of encryption, consider what minimal amount of information you really need to pass or store for later processing. There are a few approaches to that. For example, you really don't need to store passwords. You need to only store digests of those passwords in order to check them for validity. And then again, be mindful what kind of digest you are using. MD5 is no more the reliable digest for quite a bit of time by now. Then the next technique is anonymization. Anonymization is good when you don't exactly care about specific pieces of personally identifiable data, and you just need to leave some unique identifier instead, for example. But you don't really need to understand what's behind this identifier. That's kind of similar to digest in that it loses the details on the specific raw data, but it keeps the information of the identity. It tracks the identity. Anonymization can be a tricky thing, and in some cases it goes hand in hand with encryption. For example, if for whatever reason you might need to track the anonymized data back to the original source, you will have to basically implement some kind of a framework that would do effectively a public-private key cryptography. Then you might not need individual pieces of the raw data in the first place. It might be sufficient to simply pre-process and aggregate the raw data locally and then pass them to another system or to the server, to somewhere else for further processing. And those aggregated data, they are effectively anonymized. You cannot revert back to the original data set, except some cases where the number of data points is low, or cross-checks across a few data sets might pinpoint particular individual data points. So again, you have to do your homework and check out what is happening with aggregated data further on. Now, if you really need to pass raw data around and you have to think of encryption, there are a few aspects that you have to look at. First off, data at rest. You might not need to encrypt them, or you might need to encrypt them with symmetric or asymmetric cryptography. Symmetric cryptography is basically encrypting and decrypting is happening with the same key. Asymmetric cryptography, keys are different. Then there is a signing to ensure data integrity. These might go together with encryption, or you might use signing alone if you don't need to ensure that the data is concealed, and you only need to ensure that the data is pristine. It hasn't been tampered with. The situation with data at rest is a bit questionable. In some cases, you might get away without encryption, because, for example, if losing a device is paramount to losing the keys to those data, then basically you're not gaining anything from encryption. The adversary can take the keys, decrypt the data, and get exactly the same as if the data were not encrypted in the first place. When it comes to data in transfer, it's almost always a good idea to encrypt them from eavesdropping of sorts between the client and the server. just leave HTTP in the past, really. It's very much last decade. Now, what to use to encrypt data in transfer? The obvious answer is SSL or TLS, no matter how you name it. But this case only works when you are encrypting data between client and the server specifically. On the server, the data gets decrypted, the server has to either process or store them somehow, or maybe pass them on, but again, the data on the server are in unprotected form. And we will talk on the next slide about end-to-end encryption, how is that different. Finally, data in processing. Here I will just leave a note that there are modern technologies about putting the very processing of the data into a trusted enclave when there is no trust to operating system or to the hypervisor even, using hardware/software technologies such as Intel SGX, AMD SEV, and others. These technologies are still very much work in progress. They're being developed. They have significant shortcomings. And if you already know about them, then probably you know about them enough. If you don't know about them, then probably it's a bit too early for you to even learn about this. Finally, and let me just reiterate this, don't even think of bringing your own crypto implementations. Don't try to re-implement AES, don't try to implement Blowfish. That's a bad idea. Just use the implementations that are already there. If you think they are somehow imperfect, then work on making them better, if you feel qualified enough. Most probably you are not, by the way. Now, what is end-to-end encryption? Well, the answer depends on your particular setting. If we go from the definition, then basically data are encrypted at the production point and they are only decrypted at the consumption point. They are not decrypted anywhere else in between. Okay, if it were that easy, things would be much better these days. But unfortunately, you have to look at which pieces of data you can cover with end-to-end encryption. Most often, user data can be covered with end-to-end encryption. What exactly is user data is a separate, very interesting question. But let me point out that when it comes to metadata, for example, data about the relationship between several messages or events, or the metadata about the routing, it becomes a bit difficult to encrypt them because they are used to actually tackle the process of transferring the data. In Matrix, we are mostly keeping the metadata decrypted. We only encrypt user data, but we are working on making metadata more protected as well. It's a bit difficult because if you're trying to just encrypt metadata blindly, then you basically have to broadcast them across the network, which is very taxing and potentially very insecure. Now, for the next point, when you have just two clients and you have a means to establish the direct connection between these two clients, then probably the only thing that you need is TLS, because TLS gives you end-to-end encryption of sorts. Any proxy in between the service provider that tries to tamper with the web page, for example, or even a server that stands between the two clients because two clients cannot connect to each other because both of them are behind network, for example. Any proxy breaks end-to-end encryption. So you have a tough choice between either keeping it encrypted, but then the server has to somehow figure out how to route the data, for example, or keep those data unencrypted and then figure out how to protect the data in such a way that the server is not becomes a bit more reliable place. Because, for example, in Matrix, we try to treat home servers as a somewhat not completely trusted entities, which is why we're making end-to-end encryption in the first place. But anyway, the general concept is very simple. If you have two endpoints, just connect these two endpoints and pass the data over TLS. If there are more than two endpoints, if you have to route data, then probably you will need end-to-end encryption. Multipoint end-to-end encryption, when you need to send the same piece of data to different recipients, and each of those recipients have their own key, this is hard. This is really hard, and you have to avoid it if you can. You might instead try to use, for example, the broadcasting using a common public key or maybe some other means. Unfortunately, that's not the case with Matrix. In our case, we have to deal with multi-point end-to-end encryption because we have private chats with more than two users involved. Fortunately for us commons, the crypto part is done, independently verified and available in the form of open source libOlm library. That nice creature in the middle of the slide is an Olm, a blind amphibia that dwells across Central Europe. The diagram on the right describes how Matrix network is organized. Home servers in blue, they are not decrypting things. Only clients and bridges to other networks can decrypt and encrypt information in Matrix, which basically how end-to-end encryption works. And now I hand over to Tobias to talk about things in a more practical way.
Thank you, Alexei. Hi, I'm Tobias, and I'm currently implementing end-to-end encryption in a Qt application. Here's what I learned. What do we need to get going? We need a reasonably new version of Qt. That means anything newer than Qt 5.2 should be fine. Qt 6 works as well. Nothing really changes for the things we care about. Then, we need a crypto library. This doesn't necessarily need to be OpenSSL. There are many more libraries that may be better suited to your task. For example, for Matrix, we use Olm, which is tailored towards our use case. Then, when storing secrets on an end device, for example for caching them, we need a secure storage mechanism. Most consumer operating systems provide one of these. Let's start with something easy. base64. Yes, base64 is not technically a cryptographic algorithm. However, it is still very relevant since you often need it when dealing with encrypted data. This is why most cryptographic libraries provide an implementation for it. Here, in the first function signature, we can see a typical pattern. The function call to encode and decode, or encrypt and decrypt, can also be used to figure out how large the output buffer needs to be. To do this, we call the function with just the input buffer and its size, while also providing a pointer to an int that will contain the output buffer size after the function call. Then, we can allocate a buffer and call the function to actually encode the data. After that is done, we must not forget to free the allocated memory after it isn't needed anymore. All of this isn't necessary though. Qt provides the convenient functions qByteArray from base64 and qByteArray to base64. If you read their signatures, you really know everything there is to know about them. Next, what we need is randomness. Alexei will now tell you all you need to know about that.
Thanks, Tobias. So until recently, there was a bit awkward situation with random number generation, specifically for cryptographical purposes. It's fine to generate using rant, for example, a dice for your Dungeons and Dragons game. It's not exactly sufficient for crypto algorithms. Crypto algorithms expect some reliable source of random numbers, and you have to provide one. Rant doesn't give you cryptographically good randomness. C++ standard library did some work to that end. Unfortunately, depending on the platform, you might have random device of different quality. So, since random device is might be flawed to the point where it returns every time the same number, really. All those fancy things like Mersenne Twister and so on end up being useless. Now, since Qt 5.10, QRandom generator has been implemented in Qt, and it's probably your best bet. It's very easy in use. You can see it on the slide. It's literally one-liner to produce that dice from 1 to 100. And at the same time, internally, Qt goes to great lengths to try to pick the best randomness available on the platform. So that's pretty much all you need to know about randomness.
Now let's talk about hashes. Hashes are often needed, for example, for verifying file integrity or signatures. The first signature you see here was taken from OpenSSL. Its parameters are almost clear. The first parameter is the data, the second one is the length of the data. Now, the confusion starts around the third parameter. Is this what is returned? Or is the returned data actually what the function returns? The OpenSSL documentation does clear this up, though it also recommends not to use this function directly, but to use an abstraction layer over this. And to be honest, this abstraction layer is even more confusing. So this isn't really a satisfying solution. Of course, like I said, there isn't only OpenSSL, there are many more cryptographic libraries, but in this situation, we really don't need any of those. Qt also provides an implementation for cryptographic hashes in the Q cryptographic hash class. The easiest way to use this is to use the static function Q cryptographic hash and with the input data and an algorithm. Qt here provides most commonly used algorithms, so different variations of MD and SHA. There are also some other convenience functions, for example, for dealing with larger amounts of data or even the whole QIO device. Now, a quick word about hash algorithms. This is not a deep dive into which one you should use or which one you shouldn't use, but just to say so much, SHA-1 is not a secure hashing algorithm and neither is MD5. Now let's get to the interesting part. Encryption and decryption. Now there are many different cryptographic algorithms, of course. You will likely use at least 2 in your application. In this example I have written a function for encryption using RSA, but the same function could really be for most algorithms, for encryption and decryption, and it doesn't matter if it's a symmetric encryption algorithm or an asymmetric. The fundamental principle stays the same. Once again, you see this typical C function of you inputted data and its size and the key and its size, and once again you also see this pattern of call a function to know how large the output buffer needs to be. Now, such a function has different disadvantages. For example, if you don't handle the data size and the key size correctly, then your whole encryption will be broken and you don't know why. Also, error handling is done by returning an int. This is easy to ignore completely or to store it, but don't use it. So this function makes it too easy to not deal with the error. Then, once again, we need to manually allocate memory. This is fine, but it also means that we manually need to free this data, which is easy to forget, since we don't necessarily know when we don't need data anymore. What do we actually want to achieve? What we want is something like this. We have a q-byte array for the data, and a q-byte array for the key, and then we just call a function on it. Let's call it RSA encrypt. And in this situation, we have all that we need, the data and the key. The sizes are stored in there, and some other parameters that we only have for technical reasons, we don't need those. And using modern C++, namely an STD variant, we can also force the user to take at least a little bit of care about errors by explicitly acknowledging that the user doesn't care about errors by just calling std_get of the q-byte array. Now, the error type we have here is just a really thin wrapper around the error that is returned by the raw C function. It's an enum. Ideally, the enum values correspond to the ones returned by the function. So how do we actually achieve this? Well, this is now relatively easy by combining the last two examples. By now, this function should mostly make sense. One noteworthy thing is that we don't use malloc anymore. Instead, we create a byte array and reserve the size that we calculated earlier using the function call. By returning this, we can make sure that the data isn't leaked, since if the qbyte array goes out of scope, it is freed. This way we solve basically all the problems we have. Now, to wrap this up, let's talk about how to store secrets on an end device. You will typically do this for sensitive cache data, keys or access tokens. Since you shouldn't store this data unencrypted, you need some mechanism to store it without also storing the key, since that would defeat the whole purpose. Typically, this would mean asking the user for a password, which would be used as a key. Now, you don't want to do this manually, since it would lead to really bad UX if every application does this for itself, since the user would need many passwords, ideally many different passwords, and it's not a secret that when a user needs to have many passwords, they tend to be quite weak or the same, which defeats the whole purpose. For this reason, basically all major consumer operating systems provide this mechanism for the user in a way that this mechanism, let's call it keychain, automatically gets unlocked using the user's login password. Now, maintaining this for Windows and macOS and different Linux platforms and iOS and Android would be very tedious. So this is why there is an abstraction layer over this called Qt Keychain. There is an easy-to-use API that's just a read password drop for reading a password and a write password drop for writing a password. This can be either binary data or a string, so really you have every use case covered you might find. Now, you wouldn't want to use this to store large amounts of data, because it doesn't have this ergonomic kind of API like a file system has, where you can create different folders and different files in folders and have good access to it. What you want to do here is still create a file structure for your data and store the data in there, but encrypt it first using a symmetric encryption algorithm, and just store the encryption algorithm in the keychain. This way, you get the best of both worlds. You get the convenience of a file system API and the security of a keychain. Now, all that's really left for me to say is thank you for listening to our presentation and ask if there are any questions. We will be in the speakers lounge for around 30 minutes to continue the discussion. And yes, thank you.